As humans, we naturally adjust the time, the method, and the type of information we invest when trying to solve a problem. In absolute contrast, most neural links possess a static function type and computation budget that makes them approach every issue the same way. Imagine a machine learning model that adjusts independently, processing each piece of information at the speed it needs. A computer program that attacks complex problems with just the right amount of computational energy without wasting any on easy tasks. What was thought as impossible now exists. So in this video, we will learn about Google's latest brainchild, AdaTape, a giant step in the transformative journey of adaptive computation. But before we begin, be sure to hit the subscribe button and turn on notifications so you don't miss any of our upcoming videos. We are familiar with neural networks and know that they are computational systems that are greatly inspired by the structure and patterns of the human brain. A neural network works similarly to how the brain works by receiving data, passing it through neurons that weigh the significance of the input value, processing the input, applying an activation function, and sending the result to the designated layer. The feature that makes neural networks so powerful is its ability to learn from data. The network essentially learns to recognize patterns and relationships in the data it is exposed to, enabling it to perform a wide range of tasks from image recognition, language learning, visual perception, and decision-making, amongst others. Since then, the world of neural networks and AI has always been dynamic, but there's been one static aspect: the similarly unwavering computational effort expended across diverse inputs. Where the same effort is used to approach a problem, regardless of its difficulty level. For instance, some math problems are more complicated than others, and some languages are harder to learn than others. AdaTape is a neural network created through rigorous research by Fuzhou Shui and Mustafa Degani at Google, and is set to redefine this landscape. This state-of-the-art AI approach carries within it the promise of greater efficiency, adaptability, and sharper accuracy. At its heart, adaptive computation refers to a machine learning system's capacity to tweak its behavior, resonating with environmental changes. Most conventional neural networks have been somewhat rigid, spending the same computational resources irrespective of the input's intricacy. Adaptive computation aims to address specific challenges and constraints of conventional neural networks. While some networks employ conditional computation to activate a particular set of parameters depending on the input, this approach proved cumbersome and inefficient. On the other hand, various adaptive models leverage dynamic depth, adjusting the number of layers and iterations based on each input. This was worse as it led to inconsistent results and potential disruptions in the output. However, Google's AdaTape challenges this status quo by employing a transformer-based architecture that uses a dynamic set of tokens to create elastic input sequences, providing a unique perspective on adaptivity compared to previous works. AdaTape uses an adaptive tape reading mechanism to determine various tape tokens added to each input based on input's complexity. AdaTape stands out for its simplicity and efficiency, as well as being very easy to implement. Unlike other adaptive models that only adjust model depth, AdaTape introduces adaptivity right into the input sequence, making it both efficient and effective. This unique approach provides an in-demand boost in accuracy and ensures better performance across various tasks, including standard ones like image classification and algorithmic challenges. Moreover, AdaTape strikes an unprecedented balance between quality and computational cost. AdaTape enables the machine learning system to adjust its functionality according to the needs of its environment. It allocates computational resources, modulating the processing power as per the input's complexity. This makes AdaTape resource efficient and embeds an intrinsic inductive bias, aiding in tasks that have traditionally stumped neural networks, like certain arithmetic challenges. This dynamic computation offers users greater flexibility and introduces an invaluable inductive bias that can tackle previously unsolvable problems. The problem-solving potential and flexibility of AdaTape form some of the reasons that drive its appeal. For its problem-solving potential, AdaTape can, for example, effectively model arithmetic problems with different hierarchy depths, and for flexibility, AdaTape lets users tune the inference cost, allowing models to allocate more flops for a new or more complex input. And although AdaTape's foundation lies in the transformer architecture, its usability transcends its limitations. The system uses the architecture with multiple layers added to process the data, including layers that study how the tokens are related and form an output sequence. The transformer architecture, though revolutionary, has its own set of constraints. Models like T5, GPT-3, and PaLM use a fixed computational budget across samples. This means that they process a simple task with the same computational intensity and aggressiveness it would for a complex task, but AdaTape as a system judiciously allocates computational energy exactly as the task requires. AdaTape stands distinct from its predecessors and counterparts in multiple senses. It doesn't just play with the model's depth, it brings adaptivity directly into the input sequence, allowing the model to dynamically ascertain the number of tokens to add based on the input's intricacy. Such a mechanism ensures that AdaTape consistently outshines every other adaptive baseline. Further into the inner workings of AdaTape, two captivating components make it up: the adaptive function types and a dynamic computation budget. After tokenizing an input, AdaTape employs a unique vector representation of each input to decide on a variable size sequence of tape tokens dynamically. Since AdaTape is like a tape reader that reads information from a tape reader that reads data from a tape and makes calculations based on it, it can adjust itself to understand these tokens based on their complexity. It works with two tokens: the input token, which represents primary data like words and images, and the other one, which is the tape token, which holds all possible tape tokens that can work with the model. The repository of these tokens is stored in what is known as a tape bank. The creation of this bank utilizes two different methods: the input-driven bank and the learnable bank. The input-driven bank extracts tokens directly from the input, but differs in its approach from the conventional model tokenizer. It offers a dynamic perspective, potentially involving different image resolutions or abstraction levels. On the other hand, the learnable bank comes into play in scenarios where the input-driven bank approach is impossible. AdaTape employs a set of trainable vectors as tape tokens. This allows AdaTape the flexibility to retrieve tokens dynamically based on the complexity of the input. Once determined, these tape tokens are amalgamated with the original input, ready to be processed by subsequent transformer layers. Interestingly, AdaTape doesn't just use a singular feed-forward network, but deploys two distinct ones for the input and tape tokens respectively. This subtle separation led to better performance. AdaTape shines better when in use. To measure its proficiency, Google embarked on two distinct tasks: the parity tasks and the image classification. The parity task, despite its simplicity, is a notorious challenge for conventional transformers. Here, a model is required to discern the evenness or oddness of the number of 1s in a given sequence. While humans can do this easily, it has proven tricky for regular transformers to carry out since they treat long and short strings the same, which in turn causes issues. AdaTape performance in this task was nothing short of jaw-dropping. While standard and universal transformers struggled, AdaTape thrived, evidencing its unique ability to maintain a counter implicitly, something its predecessors couldn't. It achieved this by using more resources when the strings were longer and minimal resources for shorter strings, making it more efficient and accurate, particularly for longer strings. To put this in perspective, AdaTape gets 99.9% accuracy on a 256-bit parity test, while standard transformers only get barely 50%. For the image classification and efficiency task, AdaTape was benchmarked against ImagineIt 1K, and the findings revealed that AdaTape not only competed with it, but dominated. It delivered superior performance compared to other adaptive transformer baselines, proving that its innovative approach wasn't just theoretical, but immensely practical. AdaTape transcends regular computation into what is called intelligent computation. This was evident when its token selection behavior was visualized on the JFT300M validation set. The model predominantly chose central patches, aligning with the understanding that central patches often house the primary object, especially in natural images. A world where machines compute intelligently, adjusting and recalibrating in real time was once a thing of our imaginations, but AdaTape brings it right into our hands. AdaTape is a testament to Google's research prowess and also offers a glimpse of what is ahead for neural networks. AdaTape, with its adaptive tape tokens and dynamic computation, represents a shift in how we perceive and harness neural networks. Its ability to judiciously discern, adapt, and compute ushers in a new era of machine learning that is more in sync with our ever-changing world. Well, that's all there is to know about AdaTape. Let us know what you think in the comments and don't forget to subscribe. Thank you for watching.